All right. So I'm going to take a negative charge and put it there. Oh, don't want to see the field. We don't want to get distracted by the field. And then I'm going to take, so that's 1 negative nanocoulomb. This is going to be 4 positive nanocoulombs. Right. And then, as, well, I guess we don't know now, I'm going to take this little guy and move it around and just make it draw all these little lines. And for those sitting in the front, since we've never had this conversation before, what does that say right there? Equipotential. And what do you think equipotential means?
Equal amount of potential.
Equal potential. Good. Oop. Like equilateral means equal laterals. So anyway. Oh yeah, we get that weird thing looking here. Weird looking thing here. Okay. What this resembles to some people, and someone said it recently, is these kinds of things.
Oh, topograph.
Topographic maps. Yeah. Right, you look at the lines of elevation, and you know that if you let a big bowling ball from here, it's going to go downhill, right? It's going to be moving down perpendicular to the equipotential lines. These are equipotential lines, just gravitational potential, as they're projected onto a three-dimensional mountainscape, right? So it's the same idea. You can think of the equipotentials as like topographic lines on which charges will roll downhill. Right? You make the direct analogy there, with the caveat that negative charges will then do what? It will roll uphill. So positive charges roll downhill, but negative charges roll uphill. Remember, you always have the opposite where we don't have the opposite of gravity. It always attracts, but electric forces can do either. So yeah, make the direct analogy between these and topographic lines. And if it's a positive charge, right, you have high potential the closer you are to the positive charge. You have low potential the closer you are to the negative charge. In fact, you're at negative potential when you're close to the negative charge. Because KQ over R, the equation for potential due to a point charge, negative Q goes it if it's a negative charge. All right. Which means that here we got a little saddle shape, right? It's kind of like a little saddle where this is all relative, rolling downhill there, but it kind of connects there, so it's kind of, yeah. Oh, that's kind of cool. I put this configuration here because this is a cool little photo. I think it's this one. This is a cool little photo. This is lines of force and equipotential surfaces. This was drawn by hand first, calculated by hand, and then turned into this diagram here that was then published in a journal. But this is Maxwell, what he did by hand. So he actually calculated, and he just used magnitudes. He said the magnitude of A was 20, the magnitude of B -5, and so I just put 4:1 ratio with the top one being negative. And we see those same shapes. Although he has another feature here, not just the equipotential lines. We can see those, right? We can see those equipotential lines, but what else do you think he has here?
Is that field?
The field, maybe the field. What should, just based on your brains, because you guys got sharp brains, what should the relationship between the electric field and the equipotential lines look like as far as direction? Just think about it.
It should be perpendicular.
Perpendicular, yeah. It's easy to see when you look at just the point charge, right? The electric field, points this way. Well, the electric field gets weaker as you move away, and so your electric potential will be reduced as far as you get away, which means you're going from a higher electric potential to a lower electric potential. Now, often these are called electric potential lines, but they're not lines. What are they? They're not lines. This does not represent a line. It represents a
Sphere. Shell.
not a sphere,
Shell.
an equipotential surface.
Surface.
Because this is a two-dimensional analog. The equipotential surface here is not a circle, it's a sphere. Okay, because it's in 3 dimensions, there will be equal potential in 3 dimensions. An equipotential line will always start and end up closed. All the way out here. Anyway. Different configurations. Here's another one that Maxwell did with 3 charges. 15, negative 12, and 20. And so each, again, draws... Oh, yeah. Let me show you the field lines. I'm sorry. Field lines. Okay. So if you look just at where any of those electric field lines cross an equipotential surface, they will always be perpendicular. So that one's going to be perpendicular right there. This one will be perpendicular. I know that before I even do it because I've seen it. So Maxwell, needless to say, would kill for this because, oh my gosh, can you imagine calculating, KQ over R and then the distance from the charge, and then you have to do the net electric field, the net potential. It'd be tedious. We could just do it here. He would love this. Anyway. So yeah, some, and again, these are published in books, but these are based on the hand drawings that he did based on his hand-done calculations. And this is Snowmass Mountain. If you ever get a chance to get there, Snowmass Lake right there. It's one of the coolest spots in the world.
Have you had the chance to get
Yeah, a couple times. All right. So, let's relate that to what we were ending up talking about on our half day. Okay, video editor, make sure you edit this out, okay, Roman? Thanks to Roman, my dedicated and extremely skilled video editor. All right. Don't need that. So last week, we were talking about potential differences between points in space. So let me just kind of draw that again. Let's say we have a constant electric field. And you might say, well, Mr. Graham, what if it's not a constant? Well, we'll talk about that later. But we got a constant electric field. And to find the potential between 2 points, say A and B, we use the definition for electric potential, which is the negative integral from A to B of E dot dr. The negative comes into play when we're talking about potential differences between 2 points. Remember, this was based on our definition of the electric potential at a single point in space. And that electric potential at the single point had its reference to infinity, right? And so the electric potential at a point is the electric potential energy per unit of charge required to bring that charge from infinity to that location in space. I know it's complicated, but yeah, this stuff's complicated. So once again, the electric potential at a point in space is the work per unit charge required to move that charge from infinity to that position in space. And then we talked about the potential difference between 2 places, just essentially referencing the work done to bring it here from infinity minus the work done to take it there, depending on which potential difference you want. What do the potential equipotential surfaces look like here? And yes, there'll be lines as I've drawn them, but if this field filled in the whole space, it would actually be a surface, right? But what would it look like? How, if I wanted to draw an equipotential line here, what would it look like? It'd be perpendicular to the field line, so it would look like this, right? Why? There we go. So that's an equipotential line, that's an equipotential line or surface, right? And notice, and this should make sense. Objects move from high to low potential. Positive charges move from high to low potential, right? It's like they're rolling downhill on a topographic map. Well, if the electric field is pointing this way, that means there has to be some positive charge down over here creating that field. We get another Coulomb-Colombo repulsion, right? We know a positive charge will always be accelerated in the direction of the electric field. These are all several ways of saying the same thing. Is several ways of saying positive charges repel, right? That's it. And the closer you move positive charges, the more potential energy they'll have. Right? And the more potential energy per unit charge, the more potential. So yeah, good stuff, right? Making sense, kind of? Where do we find constant, because I called this a constant electric field. Where do we find constant electric fields? What charge distribution gives you a constant electric field? Literally through the entire universe, if it is infinitely large. You guys remember? Remember, this was an interesting one. What charge distribution creates a constant electric field? One that doesn't decrease as you move away from the charge. Remember, it's one of those. Yeah. Thank you. Good. And infinite, which remember we how do you find the electric field due to a ring of charge, and then you integrate that from r equals 0 to r equals infinity to find the electric field due to a sheet of charge. And so the electric field due to a sheet of charge we saw was just due to the charge density and epsilon naught, right? Yeah, so if you have an infinite sheet of charge, then at any point above that charge, the electric field will be straight up, right? Oh, why am I saying that? The electric field is the same at any point, though. What am I talking about? So it's just drawn like this from the surface, right? It's a constant electric field. No matter how far you get away. It's the same strength as it is right on the surface, right above the surface. Constant electric field. And I've told you about this before, but if I have a positively charged plate here, it's going to have an electric field that points up here and points down there. And I can double that electric field by taking another sheet of charge and maybe putting it here, but making this one opposite polarity. So if this guy's positively charged, this guy would be negatively charged, and I would double, because this guy, negative charge, the electric field points towards it, points away from this guy. So in the middle there, it's going to get a strong electric field, right? Now the electric field, because I'm sure you remember, the electric field due to a sheet of charge here turned out to be sigma over 2 epsilon naught, where sigma is simply the charge per unit area. But between here, what would it be? We're going to have 2, right? I'll draw a better picture to summarize this in a second. Just want to engage your brains.
Sigma over epsilon naught?
Yeah. You're going to have 1 from this guy pointing down. You're going to have the same magnitude pointing down there. If it's charged the same but just opposite polarity, then it's just going to be sigma over epsilon. This is a very common electric field used in electronics because this is the configuration of a capacitor. And let me draw that a little better because that was not actually done very well. So let's look at the side view though. But essentially what we're looking at is 2 infinite planes stacked on top of each other. Okay. Now I'm going to exaggerate the distance between the 2 capacitor plates just so we can have a look at what's going on inside. But we're going to assume that these guys go off to infinity. In both directions, in comparison to the spacing, and usually a capacitor spacing is a lowercase d. Usually there's stuff put in there, but we're not going to worry about it. Okay, and we're going to load the top with positive charge. And when we start studying capacitors very soon, we'll see that in a circuit, if we load the one plate of the capacitor with positive charge, the other one will necessarily attain the same charge but negative. It will necessarily happen to conserve energy and all that fun stuff. So this will happen. Now let's draw 3 field lines from the top one. Okay, we got a field line here, there, and then we got the same field lines pointing down. We already determined this. Okay. So we'll say that's E from the top plate. And we'll do E for the lower plate in purple. Well, the lower plate towards, right? Towards, same charge, but negative, and so now we get towards the bottom plate. So that will be bottom plate. Woo. This ain't the whole story. This guy creates an electric field that doesn't matter how far away you are. So this guy's electric field extends down to here. And it's still pointing away from him. So that's 3 field lines pointing away. All right, well, this guy up here creates an electric field. It goes right. It doesn't care that there's another one in there. It still creates the same electric field. And it's going to point towards that guy, which is down up here. So capacitors, conveniently, once you load charge on them, create an electric field outside of the plates of 0 and inside of double the original magnitude, or double the charge, double the field that you get from one plate. So down here, the electric field is 0 because they just cancel each other out. Up here it's 0. And down in the middle, it's going to, the electric field is going to be sigma over epsilon naught, as Jacob pointed out. Okay. This is one you either want to commit that to memory or just the electric field due to a single sheet of charge. You want to commit that to memory. It's not on the formula sheet. It's one that you probably have to do. Because what if we have a question that says something like, we're going to call this plate A and plate B. And the question says, find the potential difference between plates B and A. And if they say just generally find delta V, well, if we go delta V in one way, it's going to be different than, it's going to be negative, and the other way will be positive, right? Think delta V, think change in energy, right? Change in potential is simply change in energy per unit charge. So if I release a positive charge here, what is it going to do? It's going to accelerate down, right? So think of that. Think of that. So it probably has what type of energy here, mostly? Potential. And then that potential converts to kinetic as it travels down. So that potential energy it has, the potential energy per unit charge here, minus the potential energy per unit charge there is what we're looking for. The potential difference between the two plates. Which, if you wire these up with a 1.5 volt battery, by the way, would end up being 1.5 volts across the two plates. Here. Well, let's use our definition that we got. Delta V. Alex, I'm sorry I haven't uploaded the video for this, what we're talking about now, but check it out, later today. It's negative, or actually, let's write it like this. That's the potential at B. We want to go from A to B, minus the potential at A, which is the negative integral from A to B of E dot dr. Right? Right, Jacob? You live? Yeah, just checking. All right, real quick. E dot dr. What's that all about? That's just the definition, right? That's what is on the formula sheet. Delta V equals negative integral of E dot dr. Right? Take a look on the formula sheet. That's what you have. E dot dr. Well, if we're going from A to B, dr are displacements, right? So as I go from A to B, what is dr? Well, I'm just moving down, right? In little increments, dr. Make sense? And so I just need to integrate the dot product of the electric field and all those low drs, which they're going to be in the same direction. So E dot dr is just going to be E dr. And look, we know the electric field. It's sigma over epsilon naught times dr. That's it, and yeah, that's it. So then delta V is simply negative integral from A to, and actually, A to B of sigma over epsilon naught times dr, which is obviously the negative integral from A to B. Sorry. negative. You guys tired today? What's the integral of dr? So it's going to be negative sigma over epsilon naught times r evaluated from a to b, which is equal to, and actually, do I have a symbol that would work better than integrating r from a to b? I'm kind of, you can answer it right here. What happens when I integrate all the drs? How long is that going to be? D. So delta V is simply going to be the negative sigma over epsilon naught times D.
So you just do 0 to D instead of... If the spacing is from A to B, I named it plate A and plate B. I apologize for this. Thank you. I just call A 0 and B position D, right? And I'm going from 0 to position D as I do my integral. So yeah, this is R from 0 to D. Thank you. In general, it's this. But in this specific case, it is 0 to D. I was testing you. Good job. You passed. All right. And notice that sigma over epsilon naught is simply negative electric field times distance. So you often see this. The potential difference, negative E times D, if you're going from the positive plate to the negative plate. Because you do expect that potential difference to be negative, because your final potential is smaller than your initial potential. But if you go from B to A, then it would be positive, because your final potential would be higher than your initial potential. So it doesn't matter which way you go, you just got to be consistent. So a lot of students just remember that the magnitude of the potential difference is the electric field times the distance. Whenever you're talking about a constant magnetic field, the potential difference between any 2 points in the field is equal to the electric field times the displacement.
Whatever sigma.
Charge density, area charge density,
Right.
charge per unit area. All right.
That's a constant, right?
Yeah. Well, for whatever you'll be given it, or you have to determine it.
It
Just-
wouldn't matter anyway. It'd just be a function.
Yeah.
But then it'd have to stay in that thing.
That's what I'm saying.
So this, due to a constant electric field. Obviously, we got to be able to do what else? Non-constant electric field. So let's do that. And let's do a pretty. I really recommend you follow with this one, because this one. What's so funny over there, Ryan? Why don't you just get out? All right. So I have a. Let's do a charged insulating sphere. So charge plus Q, radius R. Yeah. Put it right here. And I'm going to impose a coordinate system. Uniformly charged. Sorry. Uniformly charged insulating sphere. And I want to know, and this is going to be complicated, but follow with me. I want to know the electric, and hopefully I don't mess up. Jillian, I might mess up. I want to know the electric field at position P. Not the electric field. I want to know the electric potential at position P. Okay? So the potential at point P is my question mark. Notice it doesn't say potential difference. When it says what's the potential, it is asking for a potential difference, but it's saying the other reference point is at infinity, right? So the potential at point P, interpret as this: the work per unit charge to bring a charge from infinity to that location. Engage your brain. as we're moving it from infinity to the surface of the charge, it's like we're doing work against a point charge, right? So that's fine. Once we pass into the insulator, then the amount of the behavior of the electric field changes, and so we got to be a little more careful there. In the words of calculus, you'd say you have a what?
Discontinuity.
A discontinuity, right? So you're going to have to integrate essentially a piecewise defined function here. But really that just means add the results of two integrals. But yeah, so that's what we got to do. How much work per unit charge does it take to bring it here? And then how much work per unit charge does it take to bring it from there to there? Now when we calculate that, if you remember, I know it's been a while, but that's how much work I need to do, but that's not general. We want to use a general force, a general field, so we say, all right, the amount of work that I need to do in bringing the charge from infinity to here is the same as the work that the electric field would do in bringing the charge from here to positive infinity, right? That's how much kinetic energy it would have by the time it got to infinity, is how much work I would have to do in storing the potential energy that would then be used to give it the kinetic energy. All right. So, using that definition of electric potential, the electric potential at a point P will be the integral from where I start, and I'm going to call my starting point position R, from R to infinity, right? Because we don't have to do any work to bring the charge any closer to the center. It's just how much work per unit charge to get it there, no more. So I stop there, right? Doing my work. But from the perspective of the electric field, well, no, the electric field does it from there and all the way out to infinity. So I'm going to go from little r to infinity and integrate the dot product of E and dr. But then I got to realize that the electric field in here and out here do not obey, because we've done this, do not obey the same equation. And this isn't a conductor, so it's not just zero inside. And so we actually have to say, I need to break this up. All right, well, I need to find out how much work it's going to take, how much work it's going to take to go from, not how much work, how much work the electric field would do in taking the charge from R to big R, which I forgot to label. Plus the amount of work that the electric field would have to do in taking it from big R to infinity. So it'll be from little r to big R of E dot dr, which will be a different electric field, plus than the one that we're integrating from big R to infinity. So those are going to be different electric fields. I got to approach each individually. It seems real complicated, guys. It's going to seem weird in your brains, but drawing the diagrams, knowing what direction we're going and where the vectors are pointing. Yeah. Anyway. All right. Let's break each one of these down individually. Let's do them separately. You're going to have a problem on a quest assignment where you have to do 3 of these, because you go through a shell as well with an inner and outer radius. Oh, yeah, that's good times. So here I got to integrate. I'm going to do this one first. The integral from little r to big R of E dot dr. Okay. What's this electric field on the inside? Do you remember how to do it? Do we know it?
No.
Do we know the electric field on the outside?
No.
Yes.
KQ
KQ over
R
R squared. KQ over R is potential. KQ over R squared is electric field. Remember, field and force are related, so they're over R squared. Potential and potential energy are related, they're over R. Okay? So, we know it out there. We should at this point, theoretically. Hopefully after today you will, because you're required to at this point. Inside, we're going to have to do some work, because to figure out the electric field inside, we got to use whose law? Gauss's law. That's my Gaussian cylinder right there. Gaussian surface right there. I should have made it green. Whatever. There's my Gaussian sphere. Notice it's a sphere, not a circle. And so if you forget, this is a good reminder. You are going to have to use Gauss's law. I guarantee it on the AP exam, on the next test in this class, because you're going to have to relate potentials to electric field. So Gauss's law, using Gauss's law, I know that the integral of E dot dA over that closed surface, and if you need a reminder, I pick an infinitesimally small area vector, dA. The electric field through that dA will always be parallel, so that E dot dA, the electric field is constant on that surface. So I just integrate dA, and I get the electric field, the constant electric field, times 4 pi r squared. Not going to go over that. That's the easy part. The harder part is the enclosed charge over epsilon naught, but hopefully this isn't too isn't too difficult. What is wrong with my brain? Hopefully this isn't too difficult for you. Because what do we use to take care of the enclosed charge? Ratio. So if you want to do ratios, that's fine. Charge density is how I like thinking of it. The charge density is charge over volume, which is 4/3 pi big R cubed. Right? That's the charge density of the big guy. But it's the same if it's uniformly charged as the enclosed charge divided by 4/3 pi times the radius of our Gaussian sphere cube. 4/3 pi cancels, and we get that the enclosed charge is, as you guys pointed out, the ratio of little r cubed to big R cubed times q. I like writing this, though, as q over r cubed times little r cubed. Because little r is the thing that just varies, right? Little r is the thing that we're integrating up to. Big R doesn't change. Big R is a constant, q is a constant. All right, so now that I have that, I have the enclosed charge. I have the electric field. Sorry. I need to figure out the electric field by combining these guys. So my electric field then is going to be, oh my gosh. What is it going to be? I'm going to have a K, right? 4 pi epsilon naught. Hold on, I got to.
KQR, little r, over.
I'm just going to write it out. I'm hurting my brain. I'm trying to think of it. So it'll be Q over R cubed, epsilon naught times little r cubed. R squared, R E is 1 over 4 pi epsilon naught times Q over R cubed times little r, right? Or, yeah, K, Q, little r over R cubed. All right. And again, we already know the electric field for outside of our big R, so we're not too worried about that. It's this one that we got to be a little more careful with. This is where we got to actually determine the electric field. This is probably what you're going to have to do on the AP exam when you use Gauss's law. You're going to use Gauss's law to calculate the electric field, and then you're going to use that electric field function to find a function for the electric potential. How do you relate them? With this equation right here. Like, almost certain that you'll do exactly that on the AP exam for one of the 3 FRQs. Okay. All right. So let's go back to this, because I want to find the electric potential at point P, but I want to do this one first. I like doing these one at a time. You can do them more than one at a time if you'd like. I mean, you can do them both at the same time if you like, or to Roman edit that out too. Okay. The integral from little r to big R of E dot dr is going to be equal to our electric field is this guy. So it's going to be the integral from little r to big R. What's E dot dr? The electric field points to the right. Dr, we are going from here to infinity, from R to infinity, because we're, again, calculating the work that the electric field will do in accelerating it off to infinity. So dr, I'll do in purple, dr is just going to be the little infinitesimally small displacement vectors as we go from R to the surface big R. Okay? Notice they point in the same direction. Just get out, Ryan. Get out. So, what's the dot product of E dot dr, Mr. Evans?
Oh, it's just
Just EDR. Yeah. So, that's going to be, yeah, because E dot dr, same direction, cosine, blah, blah, you know. So that's going to be the integral from R to R of just E times dr. We got this nice expression for the electric field. The constants in it are kq over r cubed times the integral of r dr from little r to big R. So the calculus here is pretty tricky. That's one of the tougher integrals we've had to do. What do we get? We integrate r dr. R squared over 2, evaluated from little r to big R. All right, well that's kq over big R cubed times, and this just ends up being r squared minus little r squared over 2, right? We can simplify that, and we will if we want at the end. But let's see what the other one's going to be too. As we just took care of this guy, right? So that's the work that you, Brant, would have to do in taking any charge. It's not the work per unit charge. So if there's more charge, you're going to have to do more work. In bringing a charge from the surface to that point. The rest of it is the amount of work that you would have to do in bringing a charge from infinity to that surface, right? And I add those two together. That's the total work you, Jillian, have to do, bringing that charge from infinity to R, which is exactly equal to the work that the electric force would do in moving a charge from R to infinity, which is why we use the electric field to do this calculation, because that's the general one. That's the conservative one. All right? Okay. So let's find the other one. This guy. What's the integral from big R to infinity of E dot dr? Well, E dot dr, look at what's my drs? Well, the electric field out here along my axis is always going to point that way. And I'm going from the surface to infinity because I'm doing this from the perspective of the electric field. So it's positive. The dot product is positive. So that's the direction of dr in relation to E. So this is, again, just going to be the integral from big R to infinity of E times dr. And guys, get this down. Kq over R squared. Force is inversely proportional to the distance between them. The electric field is force per unit charge. So they should have the same denominator. Right? It's kq over R squared for a point charge, which for any spherical distribution of charge, as long as you're outside of it, 1 nanometer off the surface, it behaves just like a point charge. Next time your eyes close, I'm going to throw something at you. So this integral is easy. This is just going to be kq, those are constants, times the integral from R to infinity of 1 over R squared dr, which is just R to the negative second dr, which is what? Negative 1 over R, evaluated from R to infinity, which is kq times negative 1 over infinity minus a negative 1 over R, which is kq over R. Oh, look, it's the potential due to a point charge, which is the potential energy per unit charge that you need to do, or the work per unit charge that you need to do to bring it to anywhere out here. So it's just the equation, right? kq over R. 1 over 4 pi epsilon naught times q over R. And then we just add those two together. So what is that? I got KQ because this is it's a multiple choice question, the one I'm thinking about, and you got to do some algebraic finagling in order to get your answer to look like the answer. If my memory serves me, I might need to look at it again. But I have KQ over R cubed times big R minus little r both squared over 2 plus KQ over big R. I'm going to distribute this 1 over R squared into here. Actually, I'm going to bring out the 2. So I have KQ over 2R. And then I'm going to multiply this by 1 over R. I'm going to distribute the 1 over R squared over these two terms. So I'll end up with 1 minus R little r squared over big R squared. That's correct, isn't it?
Mm-hmm.
Plus KQ over R. Well, now I can do a little factoring here, right? I can put to make it easier to see, I can put a 2 there and multiply that by 2. And I can factor one of these out, both these terms, right? Right? So I have KQ over 2R times bracket times 1 minus R squared plus 2 or KQ over 2R, what did I do that for? Times 3 minus little r squared over big R squared. That's the electric potential at point P, as long as I haven't messed it up.
It's all for one question.
Yeah.
Equals what? VP. Was that VP?
VP, the potential at P. So if you have 1 coulomb of charge there, you put in 1 for Q, and everything else, that tells you how much potential energy you'll have. Remember that potential energy is charge times potential, or actually, we'll get to this in a second. I just remind you as we're talking about this, potential is potential energy per unit charge. So if you want to know how much electrical potential energy a charge has when it's in a field, you just multiply its charge times the voltage, or the electric potential, which is why it's convenient to know that. Well, how do we get P? We got to do this process. Do we have to do it every time? No, because when we're interested in potential differences is often in capacitors, where we don't have to deal with this, because in capacitors the electric fields are constant. And when the electric fields are constant, we don't have to go through all this nonsense. You have to know how to do this, though. You have to know how to do this. Not only that, but you need to know how to calculate electric potential due to extended charge distributions, which is fun. And we're going to start doing a quest assignment tomorrow, but I'm going to have you watch a video, flipped classroom type deal. If you remember calculating electric fields due to charge distributions, you will now watch a video where Dan Fullerton will show you how to calculate electric potentials due to charge distributions. What's nice is that it's easier because there's not vectors, right? Electric potential is not a vector, and so you don't have to deal with components quite as much. Yes, there are vectors involved, but it in and of itself is not a vector, all right? That might have been, is there anything else? Note that, let's say in this diagram, this is point B, this is point A. VB minus VA. Is that negative or positive? How you know it?
Because VA is bigger than VB.
Exactly. An object here has more potential energy than an object there. A charged object. Then it has more potential here than it has there. So it has to be negative.
Is there like a charged version of like kinetic energy?
Yeah, we'll do, you release a charge at rest in a certain electric field. What's its kinetic energy? How fast is it moving after it moves so far? It's the kind of thing that they do when they accelerate subatomic particles and particle accelerators, right? They subject them to electric and magnetic fields and they crash them together at 99.9999% speed of light.
What if I shot you with a particle?
You probably wouldn't even notice it. Pretty sure you wouldn't notice it. There's like 1 billion neutrinos going through your thumbnail every second, right? And they go right through the Earth. They go right through the Earth like it's not even there.
What's a neutrino?
It's a really tiny subatomic particle that the sun emits a lot of. The same reactions that produce the photons that we get as light produce insane amounts of neutrinos. But neutrinos hardly interact with matter at all. So to detect them, they have to build these giant underground tanks of certain fluids whose molecules interact with neutrinos more often than. But most neutrinos go right through the Earth like it's not even there, going out the other side at the same speed because they move so fast. And once in a while they interact with one of those molecules, and then very sensitive detectors are there to see essentially a little flash of light that your eyeball definitely wouldn't see. Yeah, it's crazy stuff. Neutrinos are nutty little particles. They have different flavors. That's how they character. Positive, negative charges. Neutrinos have different flavors. No, they're the tau neutrino, the muon neutrino, and the electron neutrino.
Those aren't good flavors.
I think they're pretty good.
And how come Blue Bell hasn't made any flavors of those yet?
That's
they're-
actually pretty good marketing. So like the 1% population.
Yeah. All right. I guess we got a little time, so you can go ahead and get started on the video. I haven't put it on the canvas. I'll do that right now.
How long is it?
It's like 20 something minutes.
Can you promise to read it?
Subscribe.